Yeah, okay, so I made this slide when I saw all the rest of the presentations. Looks like we should be okay. You're right, so there's been a lot of great presentations today, but yeah, I thought I'd present on something a little bit different. So I'm going to be talking about generic type programming with streaming in Kafka with microservices. No, just kidding. I'm a senior full stack engineer. I work at a company called Kixeye in Victoria. We have Scala game servers, which is kind of fun. We make mid-core real-time strategy games. So if you haven't heard the term mid-core, it's not quite soft. It's not quite. It's like you take ramen noodles, put them in water for 30 seconds, and take it out. That's about the consistency of the games that we make. They're like mid-core. Yeah. So we're hiring for Scala developers. If you are willing to move from this lovely city or where you're from to Victoria, I'd love to have you. And my talk is actually going to be a literally hands-on introduction to distributed systems with Akka cluster. I really wanted to write the entire abstract as my title, but this was the longest I could get on one slide. So a little bit of context before I get going. The submission of this talk was originally to Scala Days, New York. It was a bit of a troll. The company that I worked for at the time, we got like 15 of us together and we're like, oh, we should all submit something. So each of us came up with an idea and it sounded like, a lot of them were this. And I was like, oh, everyone's smarter than me, so I'm definitely not going to be able to present that. And I saw one of the things was cool stuff. I was like, oh yeah, that's me. I can live there with Raspberry Pis. It turns out I had 7 of them already. So yeah, so I only have had a cursory knowledge of distributed systems at the time, and in particular, 0 knowledge about Akka cluster. So I was like, oh, this will be fun. I can definitely write an abstract for this at least. And then it got accepted, and that was terrifying. So the context of this talk is for those of us that don't know much about distributed systems, but you really, really need to before you have to give a presentation. That's this talk. All right, and one more thing I want to get off my chest. Putting Akka cluster on a bunch of Raspberry Pis is a bit like this. It's like a regular-sized man riding a little bike. It's hilarious and interesting, but like in no way practical. So like if someone at the end asks me, when would you use this in real life? The answer is, again, right here. Like, this is it. This is the only time. Yeah, so the agenda today is pretty simple. We're going to talk about Raspberry Pis. Quick show of hands. How many of you know what a Raspberry Pi is? Right on. Okay, so there's like one dude at the back that I made up that doesn't know about it, so we'll talk about it. We're going to talk about distributed systems. I'm not going to ask how many of you know about those. And we'll talk about Akka cluster. Okay, so, right. This is yeah, right on. This is a Raspberry Pi. Let me put this down. That's not beating. That's awesome. It's just like a normal microphone right now. That's pretty good. We killed the desk, there's no more heartbeat. Okay, so, right, so I'm supposed to, my speaker notes are telling me to do something, which I will do now. Yes, my hardware programming really paid off. So, yeah, this is a Raspberry Pi. They're small, they run on Linux, they have GPIO pins, they have USB ports, HDMI ports, networking. The most important thing are those GPIOs. So, it allows you to sort of, do stuff like that. Can anyone not see the blue blinking light behind me? If not, just come closer. That's the best I can do. All right. Okay, so like, yeah, showing you guys a Raspberry Pi is easy. It's in my hand. Like, that's it. That's the whole thing. This is a distributed system. How do you hold a distributed system in your hand? It's not very practical. So they're collections, this has gone over before, but distributed systems are a collection of smaller, discrete functional units which work in concert to achieve a higher purpose. And by definition, they don't really fit in a room. And they usually also trade simplicity for scale. So this was my best attempt at representing a distributed system. Is sort of like this. You take that sentence and you just look at it sort of one piece at a time. But if any of you have been working with these for a while, more often it might look a little bit more like this. or most often, it's like, so like that was like a little bit of overlap, right? You're like, okay, well it sort of does this, but we also need it to do this too. So more often, like the nodes in your distributed system are not gonna be easy to reason about, and more likely they'll look like this. Yeah, so that, okay, so yeah, that's my visualization of distributed systems. They're not going away, they're here. We need them to overcome latency, the number of users that use our systems, and reliability. You know what, I'm just gonna keep going. They're hard, and they're hard, like they're complex, right? So let's keep going. So in this presentation, I'm gonna attempt to take that big thing, the distributed system, and just make them seem small with Raspberry Pis, and that's the whole thing. Let's really quickly, this is gonna take a while, so I'll have to riff a little bit. But let's see. Let's start bringing up. I'm bringing up the rest of the cluster here. If I can do it in a way that looks cool, that'd be even better. So you'll start, hopefully, yeah, you'll start seeing lights. What's going on here is the communication between the first node that I brought up, that blinking blue, and the other Raspberry Pis as they come up into the cluster. So I'll just, sorry guys, I'm going the long way around the barn here. Ooh, this one's going really the long way around the barn. Hang on. Whatever, it's fine. So, yeah, there it is. Sorry, I should show you what I'm doing, but there's a wall of secrecy that I have to maintain to make this presentation a bit more fun. But yeah, we're just going to bring up the rest of those two. Okay, cool. So those are coming up. All right, so before we get too deep down the rabbit hole, I have to talk about a little bit of distributed systems theory. But with that said, I'm going to do like a really reductionist view of it, just like really bang out the parts that spoke to me in my heart. And then the rest of it, Jonas Bonner covers this in much better and greater detail. You can watch, it's a YouTube video of him presenting. It's called The Road to Akka Cluster and Beyond. And so I'm just going to pick out a few salient points, and we'll see where that gets us. All right. Cool. Right, so L. Peter Deutsch formalized 8 common mistakes developers make when working with distributed systems, but 8 is harder to remember than 4, so we're going to do 4 fallacies of distributed systems. The first one is that the network is secure. You know, there's bad people out there, so sanitize your inputs. That's like the takeaway from that. The next one is that the network is reliable. It's not. They're bad programmers, so plan on the network being unavailable because of someone else, or possibly you, earlier you. All right, the third one is, you know, there's no latency, which, you know, the speed of light really hurts us on this one. And possibly, you know, other services are taking a long time to get a message through, yada, yada, yada. Yeah, okay, that's a thing. And the last one is infinite bandwidth. So how many of you, this is a weird one, but how many of you have accidentally swallowed an ice cube whole? Okay, yeah, there's literally like dozens of us, and it hurts a lot. It's like this giant thing. If you haven't tried it, I recommend it. Or you know what, another good one, a brain freeze. Everyone's had a brain freeze from drinking too much Slurpee. It's the same thing, you know, you don't do that to your systems. Don't put a giant, just send the deltas, send what you need, no more, no less. Okay, that was not part of the original 8 fallacies, the ice cube part, I put that in. Okay, so let's talk about Fisher, Lynch, and Patterson. In 1985, most of us were younger then. All of us were younger then. They came up with a paper, and it's called The Impossibility of Distributed Consensus with One Faulty Process. I took a page from their notes when naming my presentation. And they says basically, in a distributed system, we can't tell if a process is dead or just delayed. So in a system where that is the case, it's impossible to guarantee that all nodes in a system have the same value. So this came to mind immediately, this idea that someone, anyway, yeah, that's what came to mind. Okay, continuing on, CAP theorem. 15 years later, Eric Brewer conjectured, he said that he said this theorem, which I will go into, and then it was proven later by Lynch and Gilbert. Okay, so the idea here is that reads from the system might not return the last completed write. So this is my best attempt at visualizing that. On your left, the 4 gets written into one node, but there's no guarantee that the node in the top right will actually have that value at the right time. So they talk about consistency, which is the C. It behaves as one. I'm just going to break here. I'm pretty sure most of us know this, but you should feel good while we're talking about it. That's sort of the idea here. So the idea is that the system behaves as one cohesive unit in a consistent system. Availability is that the system will respond to every request, and the P is partition tolerance, that the system will continue to work in spite of network failures. Okay, so let's talk real briefly about strong consistency. I think we're gonna fly through some of this stuff. I think Mike Nash actually in two things ago talked about the saga pattern, which I was super curious about because of this slide, and so I put that up there. But Jonas said that most SQL databases say they provide strong consistency, but like in actuality in implementation, they don't. For performance reasons, they'll punt on things. So Peter Bayless, in 2013 defined this idea of highly available transactions. I haven't dug too deeply into this at all, but it's a great jumping off point. Okay. So a quick comment on time. This was really fun for me. So learning about physical clocks, how they drift on systems. They're not a reliable way to order your events in a system, unless you're super rich and can afford a bunch of atomic clocks that will, be super good. Instead, you can use vector clocks, which keep a history of causality, but it sort of also has to carry its state around with it. It's a little bit more dense than just like a timestamp. If you want to jump more into vector clocks, Basho, the guys who do React, give a really good introduction. Just search Basho vector clocks, and they'll give you a good, there's 2 or 3 articles that go pretty deeply into that. Specifically start with why vector clocks are easy. It sounds super approachable, right? Okay, almost there. Failure detection. Remember the FLP paper. Since we can't tell if a node is late or dead, a good failure detector will just be skilled at guessing. If, we'll just be like, oh, it's probably dead. All right, so so there's 2 that I want to talk about. The first one is the fee accrual detection. I've been saying phi for 30 years, and then Jim, one of my buddies, is like, it's fee. It's like, oh no, sounded like an idiot for 30, well, almost there. I didn't say fee was not my first word, but okay, so so this failure detector keeps a response time history from heartbeat requests and uses a heuristic that can be used to guess if the node has failed, and you can configure that decision point against that. All right, so the next one is swim. This one I like more. If node A can't hit node B, it'll go up to node C and D and say, hey, can you guys hit node B? And if you can, report back what you've got to me, and then I can make a decision on if B is up or down. All right, so that's that. I'm going to skip. We might have time. Consensus protocols. In a cluster, the idea is to be able to say that yes, we're in a consistent state. There's a few different strongly consistent algorithms to maintain cluster state consistency. Paxos is the first one. I think most of us have probably heard about it, but it turns out that it's hard to understand, it's hard to implement the spec in real life, and so it's rough. The second one is Zookeeper's atomic broadcast, which has a proof of correctness, but is still kind of difficult to implement. And then Raft. So this one was sort of what got me digging deeper. They have a really good, I think it's there's a link that's in the slide notes that you can check out later that gives a really good visual introduction to Raft as well. It's also supposed to be simpler to implement than Paxos. All right, so CRDTs. I want to do the hands thing again. How many have heard about CRDTs? Okay, less than the number of people who had heard of Raspberry Pis, so I can feel a bit more confident with this one. So it stands for conflict-free data types. In a more specific naming, there's two sort of flavors. One is a convergent, what is it? Converging. You're gonna have to look this one up, but like there's two types. There's convergent and commutative. So think about a vector clock. They carry around their event causality. And so in that way, a convergent data type will always merge, but they're required to bring along their state with them. Commutative requires a reliable broadcast channel to broadcast, and then the information is applied locally. Yeah, so the nice thing about these is that if there's a network partition and a shared state needs to be merged back in after a network healing, they'll do so without manual intervention, and that's the big story there. All right, gossip protocols. This is probably the most, when you saw the lights going on, that was the cluster gossiping to each other about the state of the cluster. Right, so basically one node tells the neighbor nodes about a change in shared state. Yeah, we'll go. And it's resilient and peer-oriented, so you don't have to have like this third party maintaining the state of the nodes in your cluster. All right, so that's all of the theory. Let's actually talk about Akka cluster. How many of you have implemented Akka cluster in a production system? Yes, even less. You see we're going down, but by the end no one should raise their hand. Actually, no one raised their hand about the ice cube thing. No, there's two. Okay, we'll get there. All right, so again, from the ground up, Akka is a toolkit wrapping an actor model. The actor model sends messages back and forth with immutable copies of shared state. All right, so this is great for concurrency and distributed systems. On top of Akka, or built into Akka, is Akka remoting, which allows actors to live on remote systems. So now you have these actors running, sending messages back and forth, but now you can have one on a totally different system, and you don't really have to care. The third one is, so Akka cluster, yeah, so that brings us to Akka cluster. This is a membership service that abstracts actor systems as nodes and then manages them. Okay, so apparently this is a reliable implementation. 2,400 nodes in one cluster and able to bring up 1,000 nodes and reach convergence or be able to talk to each other, I think. I'm not sure what the finish line was there, but in 4 minutes. So like a pretty decent implementation of cluster management. All right, so the rest of the presentation, we're gonna dig into how Akka cluster implements some of that theory that we went over. All right, so the question is, how does Akka cluster gossip? The alternative, if you didn't use Akka cluster, you could use Zookeeper or HashiCorp's Surf to do this work. Akka's implementation on gossip uses Dynamo, is based on Dynamo and React's implementation, where there's preference to the nodes that haven't seen the latest version of the cluster state. So I've got some quick little circle arrow diagrams. I just coined that term myself. So outside actor or system, it wants to write 7 the state into the cluster. So this is going to be pretty basic. So 7 gets written into one of the nodes. Whether 7 gets routed in through some router or it knows one of the nodes directly, it doesn't really matter. As soon as one of the nodes knows about the state, it will then tell its neighbors. And once one of the nodes can tell that all of the rest of the nodes have seen 7, it can say that the state has converged and the cluster has reached convergence. So what actually happens behind the scenes is when one of the nodes gossips out, it sends along a set of nodes that have also seen that new state. And so yeah, once that last node can say every other node in the cluster that I know about has seen 7, I can say, hey, yeah, we're good, everyone's seen it. So this becomes important later because the leader of the cluster, which we'll get into, needs to be able to take actions like removing unresponsive nodes, being able to bring new nodes into the cluster, etc. a few extra details. Yeah, like I mentioned before, this is biased gossip, so it will sort of push out to nodes that don't have state already. It'll prefer that, but it'll also still randomly gossip to other nodes that might already have the state. One thing about the vector clocks that I talked about earlier is that they carry all that weight, the causality of the event ordering with them, which means your vector clocks can start growing. They grow as the cluster changes. This was changed in Akka 2.4. They prune the vector clock history, which means you can have a really unreliable cluster, like you can have nodes joining and leaving as much as you want without having to worry about your vector clocks growing and growing. Okay, so the next one is how it detects failure. Right. So this is how it works. So each node will monitor up to 5 neighbors. It uses that fee accrual detection. I don't know if I get into that later, but I thought I'd put that out there now. Each node will monitor up to 5 of its neighbors, and the expectation is that those neighbors should, that neighbor should reply back and say, hey, yeah, I'm up. Don't go on without me. But in this case, there's three of the neighbors sent a heartbeat request or a ping request or whatever you want to call it to the neighbor, and only 2 came back. So that node in the top right is going to say, hey, that node's unreachable. I can't reach it. And so what's going to happen is that if the subsequent nodes can't, we'll send another message to it, and if you don't get a message back, 2 things could happen. Either, depending on if you get a message back, then we can go into, on the left, you'll see the reachable state and everything's great, we continue on. If not, the leader will mark that node as unreachable, and eventually it will go into a quarantine and then into a downed state. So we'll talk about how nodes are removed from the system in a little while, but they basically are no longer considered part of the cluster. All right. Okay, so how do we make decisions about actually, I've alluded to the fact that there needs to be a decision made once a node is detected as failing. So Akka cluster uses a deterministic leader election. So election is a bit of a term that doesn't need to be provided. There's no election. It's always going to be the node on the sort. Basically, you sort the nodes, and it's the one that's first. You're the leader. Congratulations. So a node there's a bunch of states that a node can be in an Akka cluster: joining, up, leaving, exited, down, removed, and unreachable. And the leader is going to dictate the state of the cluster to the rest of the nodes based on the information that it's receiving from the rest of the nodes in the cluster. All right. So this is a quick diagram on leader election. So node F is trying to join the cluster through seed node E. So it sends a message that it would like to join the cluster, comes up, and node E will then gossip out that F is joining. Once we have convergence, the leader will mark F node as up. And once you have a new node that comes into the cluster, the actual ordering of the cluster might change, and so the leader might be reassigned to A or F. But in this case, probably A. I don't actually know what the sort is based on. I'm pretty sure it's just the address of the node. All right, so the last question we have is, how does it handle partitions? So network partitions basically look like this. You've got networks, the nodes in the cluster can communicate to each other, but oh no, now they can't. So I wonder, yeah, we'll try it on here in a second. So what happens then is that the nodes on the right think that the nodes on the left have failed, and so eventually they will be removed from the cluster. But the problem in this case is that the nodes on the left think the same things about the nodes on the right. So basically you've got these two now, this one island, this one cluster split into 2 clusters, both trying to perform the same function. And in a distributed system, that is usually a bad thing. That's not something you want. This is called a split brain. So I talked a little bit about how nodes get removed. Usually that's either going to be done automatically, so Akka cluster has this idea of like manually downing a node once it can't be found, but that just means removed from its cluster. So in this case, if we had auto downing on, the nodes on the right, or on the left, would have removed those 4 on the right without knowing what their state is. They're just like, oh, we're not going to worry about you anymore so that we can continue on. It turns out that doesn't work very well because, I mean, what happens if, so that in this case here, the nodes on the right are still going strong. But if there's another network partition, say the nodes on top and the nodes on the bottom, now you've got 3 clusters, and they're all auto-downing. So like, in the end, what you can end up with is a bunch of clusters of 1, these little islands that are like running out of control. So that's a bad idea. Don't do that. The other option is manual intervention. You can use JMX or like some other manual intervention to bring nodes down and make them stop. And then the last one, there's a feature in Akka cluster called split brain resolver, which uses strategies based on the last known cluster state to make decisions. In this case, and there's also, you could just do nothing, just leave it alone, just let it go. That's not a good idea either, because then you might have two systems starting to write to shared, like their shared state, like a shared database. Start having problems there. Not a good idea either. Okay, so one of the ways that can sort of mitigate network partitions when they come back is distributed data. This is experimental as of 2.4. Correct me if I'm wrong about the experimental part, but I'm pretty sure it was. Distributed data uses those CRDTs that we were talking about. And if you can model your data as a CRDT, then you're good to go. Like in the case of a network partition, when and if the network heals, your shared state will come back and you merged in and you'll be off to the races. So some of the data types are registers, maps, counters, and flags. So that's that. And the last thing that I want to talk about is split brain resolver. So at the end of this, I'm going to like roll back and we'll start playing with this to see if we can get a little bit more interesting stuff out of this. So each partition, so this is a split brain resolver, can use, I talked about some strategies that it can use to down itself, like to just say, I need to shut off. So in a network partition, you can use quorum size and just say, you know what, if I don't have at least 3 members, I'm just going to shut this cluster, I'm going to kill it. The leader will say, hey, let's close ourselves off. It should be running somewhere else. There's another one, keep oldest, which again just says, like, keep if my cluster still has the oldest node in the old cluster, I'll stay alive, otherwise the other cluster should kill itself. Majority, so I just have more nodes than the other side, I'll stay up. And referee, which just means like, if this particular node happens to be in the cluster, then we're good. If not, those should be shut down. So split brain resolver is a really great tool, but required is a Lightbend subscription. It is available in 2.3, while distributed data is available in 2.4. Okay, so let's go back and see what some of the things we can do with this. So that's like pretty much the end of the actual presentation. So let's go with the demo. So the first thing we want to talk a little bit about is distributed data, just because I'm using it pretty heavily in the implementation of this thing. So what I'm going to do is, let's see if I can move this over. What I've done, there we go. Yeah. Okay, so I've like set the cluster into basically like a voting mode. So what we'll do, I'm going to have to like I'm going to bring this back because I can't see it from here. But basically, I'm just going to hit some buttons on there that will start basically sending one value, either red, green, or blue, into a distributed data register across the thing. So let's hope this works. Let's go. So you'll see as like the cluster starts to converge, the data sort of goes through. So we can change that to green. And eventually that happens, which is great. And then we can also go to blue. Okay, so cool, great. Eventually that should go to, wow, yeah. Cool, so this really helps us understand eventually consistent. So yeah, so that's kind of neat. I'm going to just show you a couple other things. So one is this idea of blink. So I just have this I'm going to show you again because it's probably better. Where's my mouse? Oh, you can't even see it. Anyway, there's a button that says blink 3 times. Great. So we'll up that. Let's just show you that it works. Right on. Okay, so it works. The interesting thing is that, I'm using a feature in Akka cluster called cluster aware routing. This just says a round robin right now, but there's a bunch of other ones you can use. One of the cooler ones that works in conjunction with another feature, which is called the cluster metrics extension. It'll actually route your requests onto the cluster based on load and CPU usage of the cluster. So if one of your nodes is sort of thrashing or getting really overworked, it'll leave it alone for a while, which is a pretty cool way to route. But let's up the ante a little bit, and you know what, let's try one thing first. Let's try a split brain scenario. So I'm going to go back to those votes, and we'll just set it to red. No, blue, because blue's still leading. I pressed blue too many times, but that's fine. Now red? Yeah, good. Okay, so what I'm going to do, on the floor there's this yellow network cable. So imagine this is North America, and that is anywhere other than North America. And in a presentation setting, I don't have to remember my geography that well. And this yellow cable, imagine, is one of those important network cables. Right, so there's a bit of imagination that you have to do. But I'm going to unplug it, and then I'm going to run. So in this implementation, I have auto downing on, so I have about 60 seconds to get this done. Otherwise, the cluster on one side or the other is going to down those nodes. Unfortunately, my Akka HTTP node that's sending messages onto the cluster is on one side, and so it'll lose track of the other. It's a big mess. So I've only got 60 seconds. So this might, if you can't pay attention for 60 seconds, is all I'm saying. Just don't bother. Here we go. I'm pulling out the network cable now. All right, so now what we have is, if I'm not mistaken, a situation where one side can't listen to the other. So I'm just watching my console, which is, I'm just not going to bother showing you because of the projector's resolution. I'm now going to try voting a different color. So we'll say blue. Come on. Yeah, okay, so we have distributed data. Great. So that's working, but we have the partition. Okay. But look. Let's see DevOps do that. Just kidding. So for the camera, someone said that what I was doing was exactly like DevOps, which I do not disagree with. Okay, but interestingly enough, yeah, look at it. So we plugged it back in, the network healed, and the distributed data merged itself nicely. We had this weird state where it was oh, I think it's red, and then blue comes along and it merges itself nicely, knowing that in that event, blue is the correct value. Right, so that's that. Let's see what else we can do. So the idea of this presentation is at the end something should break. So at the end, at some point, this whole cluster should become unresponsive, which isn't really, it's not a failing of Akka cluster, it's a failing of my implementation of Akka cluster here, and it's a lot more fun, really, to demo it until it breaks, in my opinion. Okay, so let's go back to leader, if we do leader mode, that won't work. Gossip mode we've done. Oh yeah, okay, so the next thing I want to try is, let's put blink on 3,000 and just let it go. So it'll just start blinking. And then what I want to do is start voting. And what'll happen, oh no, I already sort of explained the routing, so that's not really that fun. Yeah, let's go back to the leader mode. So I think I showed you at the beginning this. So right now, this node is the leader. So it's going to be doing all of the decision making around who's up, who's down, who's coming in, who's leaving. But what I want to do is show you, this sort of is sort of a double double illustration. One is on the leader node and how it's always there. The second one is another feature in Akka cluster called Akka cluster singleton. So this is the idea when you really, really need exactly one of something. Akka cluster singleton is going to do that for you. So this is actually probably going to be the end of the demo after this. So get your questions ready. I'm just going to start basically unplugging, wrapping up the demo. So here we, let's do it. So we'll take this one and we will unplug it. So my assumption is that it's going to still keep blinking. Oh, this is going to take 60 seconds. That is a terrible idea. Okay, one. A lot like real Right, so I'm from Victoria. Okay, we're not going to do them all, but what we should see, what should happen eventually is once the rest of the cluster decides that the leader is no longer reachable, that'll keep blinking, right? Because it thinks it's fine. It's like, oh yeah, I'm doing good. It's going to auto down the rest of the other 5 nodes, and it'll keep blinking. What we should see eventually is another leader pop up, and it'll start acting on behalf of the rest of the other 5. So you know what? Let's wrap up the. Actually, you know what? Let's go back in case I missed anything. Back to the actual presentation. Yeah, cool stuff. Okay. Yeah, okay, so there's a few other, I'll just really quickly, I mentioned cluster metrics extension. Okay, so when the cluster is in a non-convergent state, so when one of the nodes can't be reached to reach convergence, the leader can't bring new nodes in. It can't perform its duties correctly. But in, I think, well, an experimental version, I think in Akka 2.4, is this idea of weekly up, where, man, it's been longer than a minute. What's going on over here? Anyway, weekly up is experimental, but it'll allow you to get nodes into the cluster, the side of the cluster that you want it to be on anyway, without having convergence. Distributed pub sub, so you can like just blast the entire cluster with a message to anyone who's listening. Cluster client is this idea, so remember when we were getting 7 to get onto the rest, we could use the rest of the cluster. You could use basically this feature that lets something not be part of the actual cluster and put messages onto the cluster. Cluster singleton we talked about. If that ever, like, if 2 of them ever start blinking, let me just like say something and I'll be like, yeah, I told you so. Cluster sharding is another one. And finally, the code for all of this is on Bitbucket, which is not as cool as GitHub. Yeah, did it? Yes! Whoa, auto down took a long time. I gotta configure that. Anyway, so yeah, we could keep doing that, but I'm not going to. Maybe I'll unplug one right before Jim's presentation. Nah, I won't do that. Okay, so in my slide notes, there's a bunch of links that I used as source for this. Yeah, again, like this, this is a completely impractical presentation and a little bit dumb, right? Like it's just kind of a thing. But what this really did for me, and it also did for a bunch of my colleagues, was give us a very tactile place that we could go, we can use like scissors or a bat to take down a node and see what happens. It's rapid iteration. I've got a quick start for in the repo so that you can, if you have 7 to what did I say, 4,000 Raspberry Pis, you could get a cluster going that way and just see what you can do. You could probably model the system that you have, given enough patience. One thing that I didn't talk about is roles inside of Akka cluster. So if you have HTTP front end, like Akka HTTP running in your cluster, you can assign them to HTTP role, and they will be your entry points and routing onto the rest of the cluster, which could be worker nodes. So it's a pretty flexible system. Yeah, and with that, the end. Thanks.